Welcome back to the deep dive. Today, we're really getting into something fundamental. It's one of those things that underpins almost everything in real-world app development: user authentication.
Absolutely. It sounds simple maybe, but architecting it right is crucial.
Exactly. We've been guiding you through building Wonderwords, this robust Flutter application, and our mission today is, well, to really master the who and the how of user identity inside your app, the whole life cycle.
Yeah, and it's so much more than just, slapping a login screen on the front.
Right. It's about building trust, managing data securely, and making sure the user has this fluid, personalized experience from the moment they open the app.
Indeed. And, for those of you listening who've maybe battled with identity management in, say, the .NET world, maybe setting up identity server, dealing with OAuth 2.0 flows, or integrating Azure AD B2C.
Which can get pretty complex.
Oh, absolutely. You'll hopefully appreciate the level of detail we're aiming for here. This deep dive into Chapter 6 of real-world Flutterby tutorials is really designed to give you that, let's call it board exam caliber knowledge.
Okay, board exam level. I like that.
We'll pull apart how Wonderwords tackles user authentication. We'll start with the basic definitions, look at how the client and server talk to each other, dig into secure storage, and even touch on some advanced state management patterns for this.
So it's about building a solid architecture for identity.
Exactly. Principles that work anywhere, really, not just Flutter.
So what does this mean for you listening? It means really getting your head around token-based authentication, not just the what, but the why it's the standard.
Yeah, why it scales, why it's secure.
And you'll learn how to store that sensitive user data emails, tokens using the platform's most secure vaults, and, maybe most importantly, how the whole app stays in sync when a user logs in or out, dynamically.
So every part reacts instantly.
Right. Get ready to go deep beyond the basics. Understand that backbone of secure user experiences. Okay, so authentication. We use that word maybe a bit loosely sometimes.
Yeah, in everyday talk, sure.
But when we're building a serious production app, it has very specific meanings, different layers, right?
Absolutely critical distinction. So let's start there. Lay that groundwork. What is authentication precisely? And then how does it differ from, say, authorization? And what about the different types of authentication we see in apps?
Okay, first principles. Define authentication.
Right. At its absolute core, authentication is just the process where something, maybe it's your app instance, maybe it's a person identifies itself and proves that identity to a server.
It answers the who are you question.
Exactly. Who are you and can you prove it? That's authentication. And crucially, this is where people often get tripped up. It's distinct from authorization.
Authorization being?
Authorization answers the what are you allowed to do question. Once we know who you are, then we figure out what permissions you have.
Okay, makes sense. Analogy time.
Yeah. The classic one works great here, regardless of platform Flutter, ASP. Microservices, whatever. Think of a secure building.
Right.
Authentication is like showing your government ID at the front desk. The guard checks it, confirms you are who you claim to be. That gets you in the building.
Verified identity.
Right. Now, once you're inside, authorization is like your access card. Does it let you onto the executive floor, into the server room, into the break room? That card determines what you can access after you've been authenticated at the door.
You can't use the access card if you didn't get past the front desk first.
Precisely. Authentication first, then authorization.
Okay, that distinction's clear. Now, here's where it gets interesting, especially looping back to our earlier deep dives. In Chapter 1, we used that API key from favcues.com. We didn't explicitly call it authentication then, but based on what you just said, was it.
You're absolutely right to bring that up. That was, in fact, our first taste of a specific type of authentication, what we call app-level authentication.
Yeah, level, okay.
Yes. That API key, that long string you got from favcues, the one we plugged in using string.from from environment with the Dart define flag.
Right, a compile time variable.
Exactly. Its job is for your application instance, the Wonderwords app itself, to prove its identity to the favcues API server. It tells favcues, hey, I am a legitimate Wonderwords client making this request.
So the app identifies itself.
Correct. It's included in the headers of pretty much every HTTP request the app makes. And the main reason favcues requires this is for server-side protection.
Ah, so they can track which app is making requests.
Precisely. They can identify your app client. If an app starts behaving badly, maybe it's a bot hammering their servers, sending way too many requests, they can detect that specific API key and block it.
Ban the abusive app.
Exactly. So it's a general credential for the application shared by all installs of Wonderwords. Critically, it's not tied to any individual person using the app.
Okay, not tied to me as a user.
Correct. Think of it like registering your application in OIF 2.0. You get a cliented, maybe a client secret. That identifies your application to the authorization server before any user interaction happens. It's about the app's identity.
Okay, so if the API key authenticates the Wonderwords app, how does FavQs know it's me, specifically, who's hitting the favorite button on a quote? How does it know to add it to my list, not just some generic app action?
And that brings us directly to the second critical type, user-level authentication. This is where the focus shifts entirely from the application to the individual human using it.
Okay, this is about the person.
Exactly. While app-level authentication is fine for general things, like fetching a public list of quotes anyone can see.
No identity needed there.
Right. But actions like favoriting, upvoting, downvoting, accessing your personal profile, these are inherently tied to you, the individual. When you favorite a quote, it's your favorite, right? Not everyone's.
Makes sense. It's personal data, personal actions.
So for these actions, the server needs two things. First, it absolutely needs to know which specific user is doing this, confirm their unique identity. And second, it needs to know if this app instance is actually allowed to perform that action on behalf of that specific user.
Okay, so it's a two-part check almost. User identity and app permission for that user.
Precisely. It involves proving that a known individual user is actively behind the request. This is where, in the .NET world, you'd be dealing with user accounts, maybe ASP.NET identity, handling password logins, issuing user-specific claims, totally separate from just registering the client app itself.
Okay, this leads to a really practical question then. If the server needs to know who I am for every single one of these personal actions, how do we do that efficiently? We can't possibly send my email and password with every single favorite click, right?
Oh, absolutely not. That would be incredibly inefficient, a huge network burden, and just a massive security nightmare. Imagine your credentials flying across the network constantly.
Yeah, bad idea. So what's the solution?
The solution is the industry standard, and it's exactly what Wonderwords uses. Token-based authentication.
Tokens. Okay, I've heard of these. JWTs and stuff?
Exactly. JWTs, JSON Web Tokens, are a very common format. The whole flow is designed to be elegant, secure, and scalable. Here's the gist.
Lay it out for us.
When you, the user, first sign in, you enter your email. Your password, the app, sends those credentials to the server. Just once.
Okay, the initial login.
The server checks them against its database. If they're valid, great. But instead of making you send them again and again, the server issues a unique access token.
This magic string.
Right. Often a JWT, it's cryptographically signed by the server, so the server can trust it later. It might contain some basic info, like your user ID, maybe some roles, and crucially, it almost always has an expiration time.
So it doesn't live forever.
Exactly. That limits the damage if it ever gets compromised. So the server sends this access token back to your app.
And the app.
The app needs to store it securely. We'll get to how in a moment, but it holds on to it. Now, for every subsequent request that needs user identity favoriting a quote, fetching your profile,
All those personal actions.
the app includes this access token in the HTTP request headers, usually as a bearer token. It also still includes the app-level API key, often.
So both keys go along.
Often, yes. App identity and user identity. When the server gets this request, it looks at the access token. It checks the signature to make sure it's legit and wasn't tampered with. It checks the expiration time.
Is it still valid?
Right. If everything checks out, the server says, okay, I know who this user is, and this token proves they're authenticated. And it processes the request, favorites the quote for you, fetches your data.
Without needing the password again.
Exactly. It makes the server stateless regarding authentication after the initial login, improves scalability massively, reduces latency, and dramatically improves security by not constantly transmitting sensitive credentials. It's fundamental. You see this pattern everywhere, including ASP.NET Core using JWT Bearer authentication middleware.
Okay, that makes a lot of sense. We've firmly established that crucial difference. App auth versus user auth. And we see how token-based systems solve the problem of identifying individual users efficiently and securely after that initial login. It's vital to remember that split when you're designing your own auth flows.
Absolutely. Which type of authentication do you need for this specific operation? Get that wrong, and you either have security holes or unnecessary complexity.
Okay, so we've got the token back from the server. It represents the user session, their identity for subsequent requests. The next logical step you mentioned is storing it. But this isn't like storing, the user's preferred theme color. This token is sensitive. It's the key to their account, essentially.
It is the key, at least for the duration of its validity. And
Yeah.
you've hit the nail on the head. How and where you store this token is just as critical, maybe even more critical, than the process of getting it in the first place.
Right, because if someone steals the key,
they can impersonate the user. Full stop. Session hijacking. Unauthorized access. It's serious. So you absolutely cannot store this token or any other personally identifiable information, PII, emails, usernames, whatever, just lying around in easily accessible places.
Okay, so let's talk pitfalls. What are the common mistakes people make?
Well, some are obvious, some less so.
Like compile time variables. We use that for the API key.
Right, but that's immediately out for the user token. Why?
Yeah.
Because you get the user token at runtime after the user logs in. It's dynamic, generated by the server then. It doesn't exist when you built the app.
Okay, makes sense. What about just, storing it in a variable in my code, an in-memory variable?
Also no good for a different reason. User experience. Users expect to stay logged in if they close the app and come back later, right?
Yeah, definitely. Relogging in every single time is super annoying.
Exactly. An in-memory variable vanishes the moment the app process is killed, so you'd force a relog in every single time. Terrible UX.
Okay, so no compile time, no in-memory. What about local storage, like a Sequoia database or shared preferences? That persists across app restarts.
Yeah, and this is where the major security risks lie. Using a regular local database or, crucially, unencrypted shared preferences, which is Flutter's go-to for simple key value stuff, like Android's shared preferences or iOS's user defaults, is a huge vulnerability for sensitive data like tokens.
Why? Isn't app data usually sandboxed?
It is, to a degree, but these standard storage mechanisms are generally not designed with cryptographic protection by default. The data is often stored in plain text or easily reversible formats within the app's private directory. On a compromised device, maybe it's rooted or jailbroken, that data can often be accessed relatively easily.
Okay, so root access breaks the sandbox.
It can, yes. And even on non-rooted devices, depending on the Android version and specific file permissions, sometimes other malicious apps might find ways to snoop on unsecured private files if security isn't perfect. The point is, these are not hardened, secure vaults. Imagine malware sniffing out your auth tokens from a plain text file.
Yeah, game over for that user session.
Exactly. For any senior developer, especially coming from environments where security is paramount, storing credentials or tokens in plain text local storage should set off massive alarm bells. Data breach risks, compliance issues like GDPR, it's just not acceptable. You wouldn't store connection strings unencrypted in a web.config, right?
Yeah.
Same principle.
Definitely not. Okay, so if shared preferences and regular databases are out for tokens, what is the right way? What's the production-ready, secure solution in Flutter? We need that digital vault.
The answer, thankfully, is quite clear and well established. You use the Flutter Secure Storage package.
Flutter Secure Storage, okay.
This package is specifically designed for this exact purpose, safeguarding small pieces of sensitive information. On the surface, its API looks really simple, kind of like shared preferences, just key value pairs. You write, you read.
Familiar API.
Exactly. But the magic, the security, is hidden in its implementation. It doesn't just write to a plain file. It acts as an intelligent bridge to the native, highly secure storage mechanisms provided by the underlying operating system.
Ah, so it uses the platform's own security features.
Precisely. Let's picture it. Flutter Secure Storage is like this abstraction layer in your Flutter code when you tell it to save a token.
What happens underneath?
On iOS, it uses Apple's keychain. The keychain is the OS-level secure enclave for secrets, passwords, keys, certificates. It's protected by system-level encryption, often hardware-backed by the secure enclave chip on newer iPhones. It's incredibly difficult for other apps or even malware to access data stored in the keychain without explicit user permission or serious system compromise. It's Apple's Fort Knox for small secrets.
Okay, keychain on iOS. What about Android?
On Android, it uses the Android Key Store system. The Key Store serves a similar purpose. It lets your app generate cryptographic keys and store them in a special hardware-backed or protected container. Crucially, your app can then use these keys to encrypt and decrypt your sensitive data, like the auth token, without the keys themselves ever being loaded directly into your application's memory. The cryptographic operations happen within the secure environment.
So the keys themselves are protected, even if the app process gets compromised somehow.
That's the goal, yes. It provides a very robust layer against key extraction and unauthorized data access. So Flutter Secure Storage gives you this nice unified Flutter API, but under the hood, it's doing the right secure thing on each platform using keychain or a key store.
That sounds exactly like what we need. So how does Wonderwords use this package? Does it just call Flutter Secure Storage directly everywhere?
Good question. While you could sprinkle Flutter Secure Storage calls throughout your code, Wonderwords employs a better architectural pattern. It implements a dedicated class called User Secure Storage.
An abstraction layer.
Exactly. This User Secure Storage class wraps the Flutter Secure Storage instance. All operations related to securely storing or retrieving user session data go through this class.
What's the benefit of that extra layer?
Several benefits. First, it centralizes all secure storage logic related to the user. If you need to change how tokens are stored later, you only change it in one place. Second, it decouples the rest of the application, particularly the user repository, from the specific implementation details of the Flutter Secure Storage package.
So user repository just talks to user secure storage.
Precisely. User repository doesn't need to know how the data is secured, only that it is secured via user secure storage. This follows the dependency inversion principle and makes the system much more maintainable and testable. You could mock user secure storage in tests easily.
Makes sense. So what methods does user secure storage provide?
It provides clear, purpose-built methods. There's upsert user info, which takes the username, email, and the token from a successful login and writes them securely using the underlying Flutter secure storage. Upsert meaning it'll update if the keys exist, or insert if they don't.
Okay, writing the data.
And then conversely, it provides methods like get user email, get user name, and crucially, get user token. These are the only ways the rest of the app can read this sensitive data back out from secure storage.
A controlled interface.
Exactly. It ensures sensitive data is always handled through this secure, abstracted pathway, never just floating around in insecure memory or files. It's a really clean and recommended pattern.
Right, we've definitely established why standard storage is a no-go for tokens and PII. And how Flutter Secure Storage bridges the gap to native secure vaults like Keychain and Keystore. Plus, the importance of wrapping that in a dedicated class like User Secure Storage for clean architecture. That's the bedrock for storing secrets correctly.
Absolutely. Get this part wrong, and much of the other security work is undermined.
Okay, we understand tokens. We know how to store them securely using User Secure Storage. Let's zoom back out a bit to the user repository. We established earlier it's like the orchestra conductor for data.
The orchestrator. Good analogy.
So how does user repository actually conduct the symphony when a user hits sign in? How does it bring together the network call to authenticate the secure storage we just discussed, and maybe other pieces too?
That's exactly its role here. The user repository, true to the repository pattern, is the central hub for managing user data, hiding the underlying complexities, where the data comes from, how it's stored from the rest of the app, like the UI layer. The sign-in function within user repository is the designated entry point for this whole process.
The function that gets called when the button is tapped.
Precisely. And it's a perfect example of a repository method coordinating multiple data sources to achieve a single cohesive goal, getting the user securely signed in and their session persisted.
You mentioned multiple data sources. What's really interesting here is it's not just talking to the network, is it? It's doing more. Can you walk us through the step-by-step flow inside that sign-in method? What exactly happens?
Absolutely. And importantly, the entire operation within sign-in is wrapped in a try-catch block. That's crucial for handling potential errors gracefully, like network issues or invalid credentials.
Good practice. Okay, step one.
Step 1, the network call. The sign-in method first interacts with the remote API property, which is our instance of FAFQSAPI. It calls the sign-in method on FAFQSAPI, passing along the email and password the user provided.
So, sending credentials to the server.
Correct. Securely over HTTPS to the server sign-in endpoint. If that network call is successful, meaning the credentials were valid, the FAFQSAPI parses the JSON response and returns a user RM object.
Our remote model.
Exactly. Its structure directly matches the API's JSON response. This user RM contains the vital pieces, the token, the email, and the username for the newly authenticated user.
Okay, network done. We have the user RM with the token. What's next?
Step 2, secure storage. Immediately after getting a successful response and the user RM, the user repository turns around and interacts with its secure storage instance.
Which is our user secure storage class we just talked about.
Precisely. It calls the upsert user info method on secure storage, passing in the username, email, and crucially, the token that just came back from the server in the user RM.
Storing the session securely right away.
Instantly. This ensures that even if the app crashes a second later, the user's session information is safely persisted in the keychain or key store, allowing them to remain signed in when they restart the app. It bridges the gap between the successful network auth and persistent local state.
So just to visualize that flow, the signing qubit, UI, calls userrepository.signin. User repository then makes a call out to favq-fapi network. If that succeeds, favq-sapi returns user RM. Then user repository makes another call, this time inward to user secure storage, passing the data from user M to be stored securely.
That's a perfect summary of the orchestration, juggling the remote source and the local secure source.
Now, that mention of user RM coming from the network brings up that critical point again, model separation.
Right.
Why don't we just pass the user RM object around the rest of the app? Why the extra step?
A fundamental aspect of clean architecture and something you'd absolutely enforce in a serious .NET application too. The user RM is a remote model. It's designed purely to mirror the network response. It might have JSON annotations, its field names might match the API's potentially awkward naming conventions.
It's tied to the external API structure.
Exactly. The rest of your application, your business logic, your UI layer, SIG and qubit, etc., shouldn't know or care about those network-specific details. If favuqs.com changes their API response structure tomorrow, you don't want that change rippling through your entire app, do you?
Definitely not. Nightmare.
So the user repository acts as a boundary. After it receives the user RM, it immediately converts it into a user object. This conversion typically happens using a dedicated mapper function, maybe called toDomain model.
And this user object is?
The user object is a domain model. It's pure, clean, and represents the concept of a user within your application's domain, independent of how the data was fetched or stored. It has no network annotations, just the data fields your app actually needs with clean names.
And where does this user model live?
These domain models reside in a shared domain models package. This makes the user model easily accessible and consistently used across all features and other repositories within Wonderwords. It prevents those leaky abstractions where network details seep into your business logic or UI.
Keeps the layers clean and decoupled.
Precisely. It's crucial for maintainability and testability.
Okay, model separation makes perfect sense. Now back to that try-catch block you mentioned in sign-in. What happens if the network call fails? Like the user types the wrong password, and why the extra step of converting exceptions?
Excellent question. Error handling is just as important as the success path. Inside that catch block, sign-in specifically looks for an invalid credentials favq exception.
An exception coming from the favcopy package.
Correct. It's a low-level exception specific to that API interaction, likely triggered by a 401 unauthorized response from the server. If user repository catches this specific exception, it doesn't just let it bubble up. Instead, it immediately throws a new, different exception. Invalid credentials exception.
Why the conversion? Why not just pass the original one along?
Again, it comes down to separation of concerns and testability. Think about it.
Okay.
The invalid credentials favqs exception is tied to the favsapi package. Your signing qubit in the UI layer shouldn't ideally have a direct dependency on favsapi. That creates tight coupling. If you swapped out favqsapi later, your UI code would break.
The UI shouldn't know about the specific network library's exceptions.
Exactly. By converting it to invalid credentials exception, which lives in the shared domain models package, just like our user domain model.
The UI can depend on domain models.
Right. Most parts of your app will depend on the domain models package. So the sign qubit can now catch invalid credentials exception, a clean, understandable domain level error, without knowing anything about favqsapi's internals.
And it can then show a specific error message.
Precisely. The signing qubit can check if error is invalid credentials exception. If true, it knows exactly what went wrong, bad username or password, and can display a helpful message like, invalid credentials, please try again. instead of just a generic, oops, something went wrong, derived from a raw network error.
Much better user experience and cleaner architecture.
Absolutely. These domain exceptions are the error handling equivalent of domain models. They create a stable, understandable interface between your application layers, isolating implementation details. It's a hallmark of robust, maintainable code, very much aligned with patterns like defining custom application exceptions in a .NET service layer.
Okay, we've really dissected how user repository orchestrates that sign-in, coordinating network calls and secure storage, using model separation, RM versus domain, to keep things clean, and converting exceptions into domain exceptions for better error handling and decoupling. That's a lot of responsibility handled cleanly.
It is. The repository pattern really shines in scenarios like this, managing complexity behind a clear API.
All right, so the user is signed in, the token is securely stored, user repository did its job. But thinking back to using wonder words, the Profile tab updated instantly, showed my username. Great. But other parts of the app, like maybe the list of quotes showing which ones I'd favorited, didn't always seem to update right away without a refresh. What's going on there? How do we make sure the entire app reacts instantly to the user logging in or out?
You've stumbled upon a classic challenge. Managing application-wide state versus screen-specific state.
Okay, global versus local state.
Exactly. A stateful widget, or even a qubit, like we used for managing the state of the sign-in screen itself, is great for managing the state of one particular screen or widget tree. But the user's authentication status, whether they're logged in or not, isn't local. It's a global concern.
Affects multiple, potentially unrelated parts of the app.
Precisely. When a user logs in, the quote list needs to know, the upvote buttons need to know, maybe the navigation drawer needs to change, the profile screen needs to update, all potentially at the same time. A single qubit tied to the login screen can't easily broadcast that change effectively to all other interested parts of the app.
So we need a different mechanism for this global state.
Yes. And this is where behavior subject from the argxstart package comes into play. It provides a really elegant reactive solution for managing and broadcasting application-wide state changes like authentication status.
Behavior subject. Okay, I know RxStart is popular for reactive programming in Flutter. What makes behavior subject special for this job? How is it different from just a regular Dart stream?
Great question. Behavior subject is powerful because it cleverly combines two key characteristics, making it ideal for representing the current state of something global. Anyone familiar with Rx.net will recognize behavior subject immediately. It serves the exact same purpose there.
Okay, what are the two characteristics?
First, value holding. This is the behavioral part. Unlike a standard Dart stream, which is often cold, it only starts emitting items after you subscribe, a behavior subject always holds a current value. It remembers the last item that was added to it.
It has a memory.
Exactly. So when a new listener subscribes to a behavior subject stream, it doesn't have to wait for the next event. It immediately receives the current latest value that the behavior subject is holding.
Okay, so a new screen loading up instantly knows the current off state.
Precisely. That's incredibly useful for UI components that need to reflect the current state as soon as they appear.
Okay, that's value holding. What's the second part?
Second, stream provision. This is the subject part. It exposes a standard stream property. Other parts of your app can subscribe, listen to this stream just like any other. Whenever a new value is added to the behavior subject using its add method, that new value is broadcast out to all current subscribers.
So it pushes updates too.
Exactly. It holds the latest value for new subscribers, and it pushes subsequent updates to all existing subscribers. It's fundamentally a hot stream that perfectly models the idea of here's the current state, and here are any future updates to that state.
Got it. It's like subscribing to a news feed that also tells you the very latest headline the moment you subscribe.
Perfect analogy. State management is essentially about observing a value and notifying anyone interested when it changes. Behavior subject nails this for global state.
So how does user repository, specifically the sign-in method, use this behavior subject to broadcast the successful login event across the app?
It's the final step within the successful sign-in flow. After the network call succeeds, after the token and user info are safely stored in user secure storage, sign-in makes one crucial call. User subject.add domain user.
User subject being the behavior subject instance managed within user repository.
Correct. And domain user is that clean user domain model we converted earlier. So we're adding the authenticated user object to the subject.
And calling add does two things, based on what you said.
Exactly. One, it updates the internal current value of user subject to this domain user. Two, It immediately emits this domain user object out to everyone currently listening to user subject.stream.
Instant broadcast.
Instant broadcast. Any widget or service listening to that stream immediately gets the new user object, signaling that the user is now signed in. That's how the profile tag, for instance, can react instantly.
Okay, that handles the update when someone signs in. But what about getting the state initially, like when the app first starts? Or how do other parts of the app listen reliably? How do they get the current user state, especially if the sign-in happened in previous session?
That's the job of the getUser function, also within user repository. This function is designed to be the single authoritative source for the rest of the app to observe the user's authentication state.
And what does it return?
It returns a stream user. The case fees means it can emit a user object if logged in or null if logged out. It's implemented using async Dart syntax for creating asynchronous generators, functions that can yield multiple values over time.
Okay, async. How did it work?
It does two clever things. First, initial load on startup. When getUser is first called, maybe when the app boots up, it checks if .userSubject.hasValue, meaning has our behavior subject been populated in this app session yet?
If it's a fresh app start, it probably hasn't.
Exactly. If it hasn't got a value yet, getUser takes responsibility for figuring out the initial state. It goes to secure storage, our keychain key store wrapper, and tries to fetch the stored email and username from the previous session. It uses future.wait to do this efficiently.
Ah, so it checks the secure vault to see if the user was already logged in.
Precisely. This is how the app remembers you were logged in. If it finds the stored details, it constructs a user object from them and calls userSubject.add with that user. This sets the initial state in the behavior subject. If it doesn't find anything, it might add null.
Okay, so it primes the behavior subject on the first call if needed.
Yes. Then comes the second part, continuous listening with yield. The core of the getUser function is the line yield userSubject.stream.
Yield, what does that do?
Yield basically says, take every single item that ever comes out of userSubject.stream and re-emit it as part of the stream that getUser itself is returning.
It forwards everything from the behavior subject.
Exactly. It connects the output of getUser directly to the output of the behavior subject. So any component that subscribes to the stream returned by getUser will, 1, immediately get the current value, thanks to behavior subject's value-holding nature, potentially primed by the initial load logic. 2, continue to receive all future updates that are added to user subject, like when sign-in or sign-out happens.
Wow, okay, so getUser becomes the one-stop shop for observing the auth state, handling both the initial check and all subsequent real-time updates.
Precisely. It's the single source of truth for authentication status across the entire application, powered by the behavior subject internally. A really elegant reactive pattern.
Okay, we've seen how indispensable behavior subject is for managing that global app-wide user state. It ensures everything stays in sync by broadcasting changes instantly and providing the current state on demand, even retrieving initial state from secure storage. That reactive approach is key to a smooth, cohesive user experience.
Absolutely. No more stale UI elements wondering if the user is logged in or not.
Right, we've got the whole flow mapped out. Sign in, secure storage, reactive state updates via behavior subject. The user feels logged in. But there's one final crucial piece. For the user to actually do things that require authentication on the server, like favoriting that, quote, the access token itself needs to get from its secure vault into the actual HTTP request being sent.
The last mile.
Exactly. How do we complete that loop? How does favqsapi, which is making the network calls, get hold of that token when it needs it?
This is indeed the final connection, and without it, all the user-specific API calls would fail with a 401 unauthorized, even if the UI thinks the user is logged in. The user repository, continuing its central role, provides one more simple but vital function: get user token.
Get user token.
Oh,
Sounds straightforward.
it is. Its only job is to ask secure storage, our user secure storage wrapper, for the currently stored user token and return it. It's essentially return secure storage.getUserToken. It's the designated getter for the token itself.
Okay, so user repository can provide the token. But how does favqsapi, which lives in a separate package and was set up way back in Chapter 1, know to ask user repository for it? How is that connection made? It feels like a dependency injection puzzle.
You're thinking exactly right. It is a dependency injection pattern. The connection isn't made within favqsapi or user repository. It's made at a higher level in the main application package, the place where you're wiring everything together. Think of it as your composition root.
the top-level setup code.
Exactly. Remember back in Chapter 1, when we set up FavQSAPI, we saw it had that setup auth headers function, and importantly, that function was designed to accept something called a user token supplier.
A user token supplier. What was that again?
It's defined as a function type. Specifically, a function that takes no arguments and returns a future string. A future that will eventually resolve to the user's token string, or null if they're not logged in or have no token. FavQSAPI doesn't know how this function works, it just knows it can call this function whenever it needs the user token for an authenticated request.
So FavQSAPI depends on an abstraction, this function signature.
Precisely. It decouples FavQSAPI from the specific implementation of how the token is retrieved. Now, in your main application package where you initialize everything, 1, you create an instance of user repository. 2, you create an instance of FavQSAPI. 3, during the setup of FavQSAPI, you call favqsapi.setupAuthHeaders, and you pass userrepository.getUserToken as the concrete implementation for that user token supplier.
So you literally pass the getUserToken function from the repository instance into the API client instance.
Exactly. You inject the specific function. Now the loop is complete. When some other part of the app, say quote or repository, needs to favorite a quote,
it calls favqsap.favoriteQuote.
Right. Inside favorite quote, FavQSAPI knows this requires user authentication. So before building the HTTP request, it calls the user token supplier function it was given during setup.
Which is actually userrepository.getUserToken.
Correct. So userrepository.getUserToken gets called, which then asks secure storage for the token from the keychain key store. That token string is returned as a future, awaited by FavQSAPI.
And FavQSAPI gets the token string back.
Yep. And it then injects that token string into the authorization, bearer token header of the HTTP request, along with the static app API key, probably in another header.
And sends the fully authenticated request off to favqs.com.
Exactly. The server gets the request, sees the valid app API key, sees the valid user bearer token, knows which app is calling and which user is performing the action, and processes the favorite request for that specific user.
That's really elegant. It keeps everything decoupled. FavQSAPI doesn't know about user repository or secure storage, just about the function it needs to call.
Precisely. It's a clean application of dependency injection using function types. It ensures that every user-specific action automatically gets the required token pulled from secure storage just in time, making the whole system work seamlessly after login. The profile tab updates because of behavior subject, and favoriting works because the token is now correctly supplied via this injected function.
Okay, that closes the loop beautifully.
Yeah.
But thinking about tokens.
Yeah.
They expire, right? You mentioned that. How does the app handle expired tokens? And what about logging out properly?
Excellent points. Real-world auth involves managing the token lifecycle beyond just getting and using it once. Wonderwords in this chapter doesn't explicitly implement token refresh, but it's a critical concept.
Refresh tokens.
Exactly. Access tokens are deliberately short-lived, minutes, maybe hours, for security. Making the user re-enter their password every hour would be awful UX. So during the initial login, the server often issues 2 tokens, the short-lived access token and a long-lived refresh token.
Okay, tokens.
The refresh token is stored just as securely, maybe even more so, as the access token. When FavQSAPI, or likely a smart HTTP interceptor within it, makes a request and gets a 401 unauthorized error indicating the access token expired,
Instead of failing immediately.
it would automatically, behind the scenes, use the stored refresh token to call a special endpoint on the server, like refresh your token. If the refresh token is valid, the server issues a new access token and potentially a new refresh token. The API client updates its stored tokens and then automatically retries the original failed request with a new access token.
All invisible to the user.
Ideally, yes. It makes the session seem continuous. This is standard OAuth 2.0 practice. If Wonderwords implemented this, user repository and user secure storage would manage both tokens, and FavQSAPI would contain the logic to handle the 401s and perform the refresh flow.
Okay, that covers token expiry. What about logout?
Logout is essentially the reverse of sign-in. When the user explicitly logs out, the user repository needs to 1. Call secure storage to delete the stored token, email username, wipe the local credentials. 2. Crucially, call usersubject.addNull to update the app-wide state, signaling that the user is now logged out. This triggers UI updates. 3. And ideally, for maximum security, it should also make an API call to the server, for example, logout or revoke endpoint, telling it to invalidate the tokens on the server side immediately.
Server-side invalidation too. Why?
Because if someone had already stolen the token before the user logged out locally, just deleting it locally wouldn't stop the thief from using the stolen token until it naturally expired. Calling the server to revoke it ensures it becomes useless immediately everywhere. While FAV-queues might not offer this, production systems usually do.
Right, covering all bases. Local deletion and server-side revocation.
Yeah.
Makes sense. That really paints the full picture. It's not just login, logout, but secure storage, state management, token supply, and handling the full token lifecycle, including refresh and proper revocation. Hashtag, tag, mega recap, and flashcards. Wow, okay, that was genuinely a deep dive. We've covered a massive amount of ground on user authentication, from the core ideas right through to the practical implementation details and architectural patterns. Let's try and consolidate that. Can you give us a mega recap of the key takeaways?
Absolutely. Let's try and distill it down. Today, we really peeled back the layers on user authentication within WonderWords, aiming for that comprehensive board exam level understanding.
Right.
We started by hammering home the difference between app-level authentication, like your static API key identifying the WonderWords app itself, similar to an Oath client ID, and user-level authentication, which is all about proving an individual's identity for doing personal things like favoriting. Getting that distinction right is job one.
App versus user.
Critical. Then we dove into token-based authentication. We saw why it's the standard using that server-issued access token, often a JWT, allows for secure, scalable, and stateless user interactions after the initial login without constantly sending passwords.
Efficient and secure.
Then a huge focus. Secure storage. We can't stress this enough. Storing sensitive tokens or PII requires more than shared preferences. We saw how Flutter Secure Storage acts as that crucial bridge, leveraging the native hardware-backed security of Apple's Keychain on iOS and Google's Key Store on Android, and the importance of wrapping this in a dedicated class like User Secure Storage for abstraction and maintainability.
The digital vault approach.
Exactly. After that, we dissected the user repository sign-in method. We saw it acting as the orchestrator, coordinating the network call, FAV-QAPI, to authenticate the user and the subsequent call to user secure storage to persist the session. We highlighted the critical architectural patterns used here: model separation, converting network-specific remote models like user RM into clean domain models like user, and using domain exceptions like invalid credentials exception to provide clear, decoupled error handling between layers.
Keeping the architecture clean and maintainable.
Precisely. And finally, we tackled application-wide state management using behavior subject from ArcStart. We saw how it perfectly solves the problem of keeping the entire app synchronized with the user's auth status. It holds the current state for new listeners and broadcasts changes instantly to all subscribers.
So the UI is always reactive.
Right. The whole system connects end-to-end when user repository.getUser token is injected into FAV-QSAPI as a user token supplier, ensuring that secure token gets automatically included in all necessary network requests. We also touched briefly on the concepts of refresh tokens and server-side logout for a complete picture.
Fantastic summary. That
Yeah.
really ties it all together. Now, to help everyone listening really lock this in, maybe some quick-fire flashcard-style questions.
Great idea. Let's test that recall. Think of these as board exam prep questions. Question 1. Okay, first up. Define the core difference, in your own words, between authentication and authorization. And give me that quick, memorable analogy we used. Question 2. Why specifically is storing a user's access token in plain shared preferences a major security no-no? What are the underlying risks? And what are the two native platform-specific secure storage systems that Flutter Secure Storage relies on? Question 3, trace the journey. Describe the complete path of a user access token starting from when it's received from the server inside user repository.signin, through its storage in user secure storage, and then its retrieval and use in an actual FAV-QSAPI network request initiated by, say, quote, a repository. Mention the user token supplier. Question 4, what's the key difference between how a behavior subject behaves upon subscription compared to a regular Dart stream? And based on that difference, why is behavior subject often the right choice for managing global app-wide state-like authentication status? Question 5. Explain the architectural benefit. Why is it good practice for a repository to catch a network-specific exception, like invalid credentials FAV-QS exception, and rethrow it as a domain exception, like invalid credentials exception? How does this help with decoupling and testability?
Excellent questions. Really makes you think through the core concepts and the why behind the patterns. This whole deep dive really highlights how building robust apps isn't just about writing code. It's about making very deliberate, secure, and scalable architectural choices.
It really is. Every piece connects. How you handle identity touches everything: security, user experience, maintainability, scalability.
So, thinking ahead,
Mm.
we've seen how behavior subject works well for managing state within this single Wonderwords app instance.
Mm-hmm.
But what if? What if Wonderwords grows? What if it needs to talk to multiple different backend services, maybe microservices? Each might even have its own way of handling authentication.
The distributed systems challenge.
Exactly. How might you take these principles, reactive state, secure storage, token management, and apply them when managing a user's identity and session across a whole landscape of separate services, maybe involving protocols like OFI 2.0 or OpenID Connect in a more complex way? How do you keep that experience seamless and secure when identity is spread out?
That is a fantastic question to ponder. It moves into the realm of single sign-on, SSO, federated identity, managing token lifetimes, and revocation across multiple relying parties. It definitely builds on the foundations we discussed today, but adds significant complexity. How do you ensure security, responsiveness, and that same seamless user experience when the backend is no longer monolithic?
Something for our listeners, especially those senior devs, to mull over as they architect their next generation of real-world applications.
Indeed, a fascinating challenge for the future.